Hey everyone, welcome back to the channel. If you're preparing for the Databricks Certified Data Engineer Professional exam, you're definitely going to want to stick around for this one. Today, we're looking at a question that seems simple at first glance, but trust me, it has a way of catching people off guard during the exam. And once you understand the reasoning behind the correct answer, you'll be able to handle several similar questions with no problem at all. So let's dive right in. Let's look into the fifth question. A data engineering team is ingesting binary files from cloud storage into Delta Lake for further processing. Which strategy is recommended? Here are the options. 1. Use Spark Autoloader with binary file format and append to Delta Lake. 2. Manually read each binary file in a Python loop. 3. Convert binary files to text externally before ingestion. 4. Store binary files in S3 or ADLS and query them directly using ad hoc Spark sessions. All right, those are the choices. No explanations yet, just the raw options. Now let's walk through them together because there's some good exam logic behind each one. Now, this one's really interesting because when people see the words Delta Lake and ingestion strategy, they jump straight to using autoloader or structured streaming or something involving Delta tables. And honestly, that's fair. Databricks spends a lot of time teaching you about structured ingestion patterns, schema evolution, constraints, ACID transactions, all that good stuff. But hang on, because this part's super important. Binary files are a completely different story. You might be wondering why this happens. Why aren't binary files treated the same way as structured data, like JSON or CSV or Parquet? Why don't we just load them into Delta tables the same way? Let's break that down together. Binary files aren't something you merge, update, or delete inside a table. They're not something you query for individual fields. They're basically blobs, large, raw objects, the kind of stuff like images, PDFs, audio files, medical device output, manufacturing machine logs, compressed sensor dumps, all the kinds of files that don't fit neatly into rows and columns. And once you realize that, suddenly a lot of the options start to make more sense. So let's walk through them one by one in a natural flow. Option 1 is autoloader with the binary file format. Now at first glance, this sounds reasonable. Autoloader is great. It handles incremental files, it's scalable, it's fault tolerant. It seems like the perfect choice for almost any ingestion workload. But here's the thing. Loading binary files into Delta Lake isn't actually recommended. There's no real benefit. You can't enforce schema. You can't do operations like updates, deletes, or merges on the binary content. You end up storing large blobs inside Delta, adding overhead without gaining anything meaningful. So autoloader isn't the direction Databricks wants you to go for this scenario. Then we have option 2, manually reading each binary file in a Python loop. This one is just painful. It doesn't scale. It doesn't use Spark's distributed power. It's slow, error-prone, and the exam definitely expects you to avoid answers that rely on manual looping. Anytime an option suggests processing cloud files one by one with Python, you can almost always rule it out. Option 3 says convert binary files to text externally before ingestion. Now, this is one of those red flag options that exam writers love to throw in. This basically means corrupting the data by forcing it into a format it wasn't meant to be in. Also, you can pretend it's structured. It's not realistic, not scalable, and not something Databricks would ever recommend. So far, all three options don't feel quite right. Which brings us to the last one. Option 4, store binary files in S3 or ADLS and query them directly using ad hoc Spark sessions. And this is the one that lines up perfectly with Databricks' best practices. Binary files should stay where they belong in object storage. Cloud storage is built for this kind of workload. It's infinitely scalable, cheap, resilient, and optimized for storing large blobs of data. Spark can read binary files directly on demand. You don't need Delta. You don't need schema enforcement. You don't need transactional guarantees. You just process them as raw files whenever necessary. So what does this really mean for you? It means not every ingestion pattern needs to be forced into Delta Lake. One of the biggest things Databricks wants data engineers to learn is when to use Delta and when not to use it. Structured data? Absolutely. Semi-structured data? Definitely. Slowly changing data, audit logs, transactional pipelines? Perfect. But binary blobs? Nope. Let them live in object storage. Now, this is the part that really makes the exam easier. Once you understand that principle, any question about binary data becomes almost predictable. If you see options involving Delta Lake for binary ingestion, they're probably wrong. If you see looping in Python, that's definitely wrong. And if you see converting binary to text, run the other way. But if you see something about keeping binary files in object storage and letting Spark read them directly, that's your answer every time. So option 4 is the correct answer. Before we wrap this up, here's the takeaway I want you to remember. Delta Lake is powerful, but it's not the right home for raw binary content. Object storage is, and Spark can read those files whenever you need them without the overhead of maintaining delta tables that don't actually give you any benefits for this use case. Let's look into the 7th question. A company plans to change the clustering keys on an existing Delta Lake table with liquid clustering enabled. What are the recommended steps? Here are the options. Alter table to set new clustering keys. Run delete and merge on the table to recluster all files. Use incremental optimize for new and modified data. Schedule optimize full carefully based on table size and inserts. Recreate the table from scratch with the new clustering keys. All right, those are the choices. Before we get into which ones are correct, let's break this down together because there's some very specific exam logic here. Now, this one's really interesting because a lot of people assume that changing clustering keys means you have to rewrite the entire table immediately. That's not the case, and understanding that distinction is critical. So let's start with option 1, alter table to set new clustering keys. This is really important. When you change the clustering keys with alter table, you're updating how future inserts and updates will be clustered. But hang on, because this part's super important. Existing data doesn't get rewritten automatically. It stays the way it is until you run an optimize operation. This is a subtle detail that exam writers love to test. Option 2 says run delete and merge on the table to recluster all files. Now, this might seem reasonable at first glance. After all, if you want everything to match the new keys, why not just force it, right? But you might be wondering why this is a bad idea. Well, using delete or merge to force reclustering is unnecessary, and it can actually disrupt Delta Lake's ACID guarantees. It's not a recommended practice. Think of it like trying to force a shortcut where a controlled method already exists. It creates more risk than benefit. Next, option 3, use incremental optimize for new and modified data. This is one of the golden rules of liquid clustering. Incremental optimize focuses only on new or modified files. It gradually enforces your new clustering keys without touching the entire table at once. It's efficient, it's safe, and it aligns perfectly with Delta Lake best practices. This is exactly what you want for ongoing operations. Option 4 is to schedule optimize full carefully based on table size and inserts. This is also a best practice. For very large tables, running optimize full immediately can take hours and consume significant resources. By scheduling it thoughtfully, considering how much data you're inserting and how big the table is, you maintain system performance and avoid long-running operations that could disrupt workloads. Finally, option 5, recreate the table from scratch with new clustering keys. Now, this one's a classic exam trap. While technically possible, it's completely unnecessary in a real-world scenario. Recreating the table is time-consuming, risky, and inefficient, especially when Delta Lake provides built-in mechanisms like alter table and optimize to handle this safely and incrementally. So what does this really mean for you? The correct answers here are options 1, 3, and 4. Alter table updates future clustering behavior, incremental optimize handles new and modified data efficiently, and scheduling optimize full carefully ensures you don't overwhelm the system. Delete, merge, and recreating the table, those are red flags. Avoid them. Now let's take a step back. This question is not just about memorizing commands. It's about understanding how Delta Lake liquid clustering works. You need to think about efficiency, risk, and system performance. When you're in the exam and you see a question like this, always ask yourself, what will happen if I rewrite the entire table versus handling this incrementally? The safest, most efficient choices almost always follow Delta Lake's built-in mechanisms. To wrap this up, here's the key takeaway. Changing clustering keys doesn't mean rewriting everything immediately. Use alter table to set future keys, apply incremental optimize for new and modified data, and schedule optimize full carefully for large tables. Avoid shortcuts like delete, merge, or recreating tables from scratch. That's how you maintain performance, preserve ACID guarantees, and follow best practices, exactly what the exam is testing. This question is a great one because it tests a real-world skill that's important when working with Lakeflow declarative pipelines. You'll see why understanding this can save you a ton of headaches and why it's exactly the kind of thing examiners love to test. So let's dive in. Let's look into the question. During pipeline development, you want to validate the correctness of your Lakeflow declarative pipeline source code without triggering updates to tables. Which features should you use to accomplish this efficiently? Here are the options. Dry run updates, which check syntax, dependencies, and pipeline configuration without updating any datasets. Run a full pipeline update in development mode to test the tables interactively. Create a temporary cluster and execute the pipeline with sample data to monitor outputs. Schedule a production job immediately and monitor logs after completion for errors. All right, those are the choices. No explanations yet, just the raw options. Now let's walk through them together because there's some very specific reasoning behind which one is correct. At first glance, you might think, hey, why not just run the pipeline in dev mode or spin up a cluster and test things? And that makes sense. In the real world, you do want to see your pipeline work end to end. But hang on, because this part's super important. The question specifically says without triggering updates to tables. That little phrase is the key. So let's break that down together. Option 1, dry run updates. This is exactly what it sounds like. Dry runs allow you to check your pipeline syntax, resolve dependencies, and validate the DAG, directed acyclic graph, of your pipeline. The really nice part is that it doesn't actually execute any updates or write to any tables. It's like running a rehearsal for a play. You get to see if everything is in the right place, cues are correct, and no one forgets their lines, all without changing anything on the actual stage. This makes it extremely efficient for development and testing. Option 2, run a full pipeline update in development mode. Now, at first glance, this seems reasonable. You get to see the pipeline in action, which is often what we want. But you might be wondering why this isn't ideal for this scenario. The problem is that it does trigger table updates, which the question explicitly says we want to avoid. Plus, running full updates can consume unnecessary resources and might make debugging more complicated. Option 3, create a temporary cluster and execute the pipeline with sample data. Again, you might think, well, that sounds safe because it's not the production cluster. But the issue here is complexity and overhead. Spinning up a cluster, even temporarily, adds time, cost, and extra steps. It also doesn't fully emulate the pipeline behavior without writing data somewhere, so it's not the most efficient method for quick validation. Option 4, schedule a production job immediately and monitor logs after completion. Now, this is almost like a trap answer. Sure, you can monitor logs and catch errors, but scheduling a production job to test your pipeline is unsafe. You could end up modifying live data sets, causing inconsistencies, or introducing errors into the real environment. It's risky and definitely not something you want to do in a development or exam scenario. So what does this really mean for you? The correct answer here is option 1, dry run updates. This allows you to iteratively validate your pipeline code without touching any tables. You can catch syntax errors, missing dependencies, or DAG misconfigurations before they ever reach a live environment. It's fast, safe, and exactly how Databricks expects a professional data engineer to approach pipeline validation. Now, the key takeaway, when you see questions like this, always pay close attention to qualifiers like without triggering updates or efficiently. These words guide you to the safest, most professional approach. In the real world, dry runs are invaluable because they let you catch mistakes early, save resources, and maintain data integrity. To wrap this up, for Lakeflow declarative pipelines, use dry run updates to validate your source code. Avoid running full updates, spinning up temporary clusters unnecessarily, or touching production tables for testing. Remember, the exam isn't just testing your memory of features, it's testing whether you understand best practices and safe development workflows. All right, that's it for this one. If you found this breakdown helpful and want more exam prep tips for Databricks Certified Data Engineer Professional, make sure to like this video, subscribe to the channel, and hit that notification bell so you don't miss any upcoming practice questions. Keep practicing, keep learning, and you'll be ready for the exam with confidence.